Before we get into the nitty-gritty of tornadic radar signatures, let's first discuss how to properly identify horizontal wind shear using velocity data. In most cases, shear signatures, especially those that are important in storm chasing, come in the form of couplets, which are highly localized features in which an area of enhanced inbound velocities is immediately adjacent to an area of enhanced outbound velocities. Just a quick refresher, inbound velocities, which indicate particles moving toward the radar, are represented by greens, blues, and pinks, while outbound velocities indicate particles moving away from the radar and are represented by reds, oranges, and browns. When analyzing shear signatures, it's critical to know where the radar is located with respect to the couplet itself. In all of the upcoming examples, let's assume that the radar is located at the bottom of your screen, i.e. due south of the feature of interest. Horizontal shear can take on the form of convergence and divergence. Convergence occurs when winds come together. In radar velocity data, that would look something like this, with the area of inbounds on the far side relative to the radar and the area of outbounds on the near side. You can see how this represents convergence. The winds within the couplet are blowing toward each other. On the other hand, divergence happens when winds spread apart. Therefore, a divergent signature is just the opposite of a convergent signature, with the area of outbounds on the far side relative to the radar and the area of inbounds on the near side. The winds are blowing apart or diverging. If you were to draw an axis directly through the middle of a convergence or divergence couplet, it would be oriented parallel to the radar beam. An example of a phenomenon that produces a divergent signature in velocity data is a downburst.
Seats are currently on sale for our 2027 Storm Chasing Tour. Secure your seat now for this once-in-a-lifetime experience. Link in the description.
Now let's add rotation into the mix. Cyclonic rotation occurs when winds spin counterclockwise around a center. In radar velocity data, that would look like this. If you were looking at the cyclonic couplet from the radar site, the area of enhanced inbounds will be to the left of the area of enhanced outbounds. In contrast, anticyclonic rotation occurs when winds spin in a clockwise direction around a center, which on radar looks like this. The area of enhanced inbounds is always to the right of the area of enhanced outbounds when viewed from the radar site. This time, if you were to draw an axis through the middle of a cyclonic or anticyclonic couplet, it would run perpendicular to the radar beam. Mesocyclones and tornadoes combine aspects of both convergence and rotation, which is typically cyclonic, so the axis of a couplet associated with a mesocyclone or tornado may not always be purely perpendicular to the radar beam. That brings us to a special kind of couplet called a tornado vortex signature, or TVS. As its name suggests, a TVS is a concentrated area of intense rotation evident in velocity data that suggests the presence of a tornado. Given the variety of different sizes, shapes, and intensities that tornadic vortices can exhibit, there are few official thresholds defining exactly what constitutes a TVS. In a very general sense, the smaller and/or more intense a couplet is, the more likely it represents a tornado, but it depends on the environment and the couplet's distance from the radar, among other factors. The intensity of a TVS is calculated by finding a variable called delta V, which is the difference between the maximum outbound pixel and the maximum inbound pixel within the vortex signature. Delta V does not correlate directly to tornado intensity. Instead, rotational velocity, or VROT, is a much better estimator of tornado intensity from radar data. VROT is simply half of delta V. In this example, I found, using this program's inspector tool, that the maximum outbound velocity within this TVS is 97.3 miles per hour, and the maximum inbound velocity is negative 52.6 miles per hour. Plugging these values into our equation, we get a delta V value of 149.9 miles per hour. Dividing this by 2, we get a VROT value of about 75 miles per hour. National Weather Service radar algorithms identify a TVS as a rotational couplet that has a delta V greater than or equal to 90 knots, or about 100 miles per hour, at a range of less than 35 miles from the radar site, or greater than or equal to 70 knots, or about 80 miles per hour, at a range of between 35 and 65 miles from the radar site. Because the radar beam increases with height above Earth's surface the farther out it travels from the radar, tornadoes and supercells that are even more distant from the radar may evade detection, and any rotational signature that does appear might only be attributed to the parent mesocyclone, given how high up into the storm the radar would be sampling at its lowest elevation angle. Describing a vortex signature by both its intensity and size is preferred. For example, if a rotational signature close to the radar meets the TVS criterion of a 100 mph delta V, but the distance between the maximum inbound and maximum outbound pixels is several miles, you may only be observing a mesocyclone rather than a tornado. Generally, when the distance between the maximum inbound and maximum outbound pixels of a couplet is less than or equal to about 2 kilometers, about 1.25 miles, you are dealing with a TVS. This should not be considered a hard and fast threshold, as there are many exceptions, but it's at least a general rule of thumb to utilize when out in the field. Sometimes TVSs can be a bit tricky to identify, but there are some things that can help you ascertain whether or not a rotational signature is legitimate. As previously mentioned, knowing where the radar is located relative to the couplet in question is key. If you see a couplet but are unsure whether or not it's rotational in nature, identifying where the radar site is will lend clarity to which direction the winds are blowing within the couplet. For example, at first glance, this might look like a legitimate rotational signature. However, given that the radar is located just northwest of the couplet, we can clearly tell that this is a divergence signature. Also, TVSs are always symmetric across a radial, whereas convergence and divergence signatures run along radials. If an apparent rotational signature looks like a TVS but is not split in half by a radial, with most or all of the outbounds on one side and most or all of the inbounds on the other, it is not a true TVS. TVSs are generally persistent features as well. In the vast majority of cases, they last longer than one radar scan and therefore can be tracked over time. If a possible rotational signature appears in one scan and completely goes away in the next, that rotational signature is likely bogus. Similarly, they should possess vertical continuity as well. As you go up an elevation angle, there should be a TVS or at least some manifestation of a robust mesocyclone. Don't be alarmed if the vortex signatures aloft are displaced from the low-level vortex signature. This signifies the tilt in the supercell's updraft and, in turn, the entire vortex, induced by deep layer vertical wind shear. The exception is for non-supercell or landspout tornadoes, which are not associated with apparent mesocyclone. Landspout tornadoes begin at the ground and are quite shallow, so they may only be sampled by a radar at its lowest elevation angle. A TVS's location within a storm should also make sense. In a supercell, it should be located at the tip of the hook echo, or if a hook echo doesn't exist, near the rear flank of the storm. In the northern hemisphere, this tends to be on the supercell's south or southwest side. Sometimes, in lieu of a hook echo, you may see a bounded weak echo region, similar to what we discussed in episode 2, colloquially called a donut hole. As we discussed in the previous episode, tornadoes tend to occur at the interface between the forward flank and rear flank downdraft gust fronts. Often, you can make out the rear flank downdraft gust front in reflectivity data as a fine line draped downward from the tip of the hook echo, as well as in velocity data as a subtle convergence boundary wrapping into the TVS. Sometimes, anticyclonic tornadoes can develop near ongoing tornadoes, often along the rear flank downdraft gust front. On occasion, couplets will appear in the forward flank precipitation core, or even in the precipitation-free inflow notch of a supercell displaced from the hook. These are illegitimate TVSs and are the result of radar artifacts, which we'll discuss in a future episode of this module. In a squall line, TVSs are often coincident with small kinks in reflectivity along the leading edge of the line, or in supercells embedded within the line. TVSs in squall lines can often be difficult to detect, as they often appear small, asymmetric, and fairly weak, and they tend to be quite transient in nature. Sometimes an area of cyclonic rotation can develop at the northern end of a bow echo, which is called a bookend vortex. Bookend vortices can produce significant damaging winds and tornadoes. Standard base velocity measures the target's velocity with respect to Earth's surface, which is stationary. However, storms and storm-scale phenomena, like tornadoes, almost always move with respect to Earth's surface. Base velocity estimates the portion of a target's velocity that's moving directly toward or away from the radar, i.e. along a radial. This also includes the motion of the parent storm, which can make it difficult to obtain proper velocity measurements. For example, if a target within a storm has a velocity of 40 miles per hour, in essence the storm has 40 mile per hour winds, and the storm is moving directly at the radar at 30 miles per hour, the base velocity product will estimate the target's velocity to be 70 miles per hour, which is erroneous. This can mask rotational signatures like TVSs, making them difficult to analyze properly. To combat this, we can use a product called storm relative velocity. This is just like the base velocity product, only with storm motion subtracted out. So, in our example of a target moving at 40 miles per hour within a storm moving directly at the radar at 30 miles per hour, the storm relative velocity product would estimate that target's velocity to be a more accurate 40 miles per hour because storm motion has been subtracted out. Storm relative velocity is especially effective in identifying TVSs in QLCSs, as well as in situations in which supercells are moving very quickly. Let's take a look at an example. On the left is base reflectivity, and on the right is base velocity. Here we have a supercell thunderstorm moving at 55 miles per hour away from the radar site, which is located just off the bottom left corner of the image. As you can see, the supercell possesses a well-defined hook echo, as denoted by the yellow arrow. At the tip of the hook, we see an area of strong outbound winds, but very little in the way of inbound winds. At first glance, you might overlook this signature given its asymmetric nature, but when we switch to storm relative velocity, we see a much clearer depiction of a TVS, with an area of strong inbounds adjacent to an area of strong outbounds. This makes sense. Let's say our inbound winds within this TVS have a velocity of 55 miles per hour moving toward the radar. With a storm motion of 55 miles per hour away from the radar, the resultant base velocity reading would be an erroneous 0 miles per hour, and our outbound velocities would be drastically overestimated. With storm motion factored out, we get a much more realistic depiction of the velocities within the couplet and a much clearer indication of a TVS. At the time of this radar image, an EF3 tornado was ongoing, which highlights the importance of using storm relative velocity rather than base velocity in tornadic situations. In addition, TVSs within QLCSs can sometimes be difficult to ascertain given their typically weak and brief nature. While this can be the case regardless of the velocity product used to analyze them, storm relative velocity can help in this regard. Base velocity is more effective in identifying straight-line wind gusts, including downbursts, particularly at the lowest elevation angle. One issue that can plague intense TVSs is called velocity aliasing. Recall from the first episode of this module that every radar has a maximum unambiguous velocity, or Vmax. If a target is moving so fast that it exceeds the amount of phase shift the radar can detect, its velocity will become ambiguous, meaning that the radar might think that it's stationary or moving the opposite direction at a much different velocity than what it actually is. Because it applies to both inbounds and outbounds, the maximum unambiguous velocity, which is also called the Nyquist velocity, dictates the range of velocities that can be observed without this ambiguity. In other words, velocities that fall between positive and negative Vmax will be estimated accurately in velocity data. This range is called the Nyquist interval. Sometimes, winds within a TVS can be so intense that they exceed the Nyquist velocity, which causes them to exhibit much different velocities on radar than they actually have. For example, let's say a radar with a Nyquist velocity of plus or minus 70 miles per hour is sampling a TVS. Let's say a target within the TVS has an actual outbound velocity of 100 miles per hour. The radar will attempt to estimate the target's velocity, but it maxes out at 70 miles per hour. To compensate for this, the velocity folds over to the other end of the Nyquist interval and continues along the interval to account for the remainder of the velocity. In this case, the Nyquist velocity is 30 miles per hour shy of the target's actual 100 mile per hour velocity, so we'd go an additional 30 miles per hour, which gives us a radar estimated velocity of negative 40 miles per hour. So, the radar thinks that our target, which is actually traveling at 100 miles per hour away from the radar, is instead traveling at 40 miles per hour toward the radar. Let's say our outbound target was traveling at 150 miles per hour. The radar would read it as 70 miles per hour plus another 70 miles per hour plus the remaining 10 miles per hour, giving us an output of 10 miles per hour away from the radar, much different than the target's actual velocity. This can make TVSs and other signatures of intense winds difficult to properly analyze. Instead of a symmetric signature between adjacent enhanced inbounds and outbounds, you might see inbounds where there should be outbounds and vice versa, as in this example. Thankfully, all National Weather Service radars use an algorithm to de-alias velocity data, so most of the time we don't have to worry about velocity aliasing. Still, the algorithm can leave behind some aliased velocities at times, so it's good to know what to look out for. Another product that can come in handy when trying to identify a TVS is spectrum width. In reality, a single radar pixel can contain millions of targets, each with its own velocity. The radar averages the velocities of all the targets within a single pixel to come up with the velocity value for that pixel. Spectrum width is the range of velocities within a single radar pixel. In situations of high atmospheric turbulence, such as within a tornado, targets tend to move in a varied, chaotic fashion. The range of velocities in a given pixel is large, and therefore spectrum width will be enhanced at the location of the TVS. The various targets within the vortex, both meteorological and non-meteorological, have different aerodynamic qualities, yielding a wide range of velocities and high spectrum width. Spectrum width also does well identifying boundaries, especially when they may be shrouded by precipitation in reflectivity data. Prior to the advent of dual polarization radar, meteorologists were unable to confirm whether or not a tornado was in progress solely from radar data. However, because dual polarization radar can analyze the horizontal and vertical characteristics of targets, we can now tell whether or not debris is being lofted by an ongoing tornado. This is manifested in a feature called a tornado debris signature, or TDS. TDSs appear in correlation coefficient data as a small area of lowered correlation coefficient co-located with a tornado vortex signature. Correlation coefficient tells us how similar or correlated the targets are that a radar samples. In a tornado, each piece of lofted debris has different horizontal and vertical characteristics, as well as different orientations. This dissimilarity yields a decrease in correlation coefficient within the tornado. Tornadoes can loft debris quite high into the atmosphere, so a TDS at the lowest elevation angle may also be accompanied by a debris signature at higher altitudes as well. In fact, if a tornado vortex signature is within 80 miles of a radar site, tornado intensity can be estimated using a combination of rotational velocity and the maximum height of the TDS. As illustrated in this chart, in supercells, weak tornadoes, EF0 to EF1, tend to feature a rotational velocity at or below 40 knots or 46 miles per hour and a maximum TDS height under 8,000 feet above radar level, while violent tornadoes, EF4+, typically have VROTs in excess of 85 knots or 98 miles per hour and maximum TDS heights of over 18,000 feet above radar level. Some of the most intense tornadoes can loft debris over 20, 30, even 40,000 feet above ground. In addition, the rotational velocity thresholds are slightly lower for QLCS tornadoes, and there can be some overlap in VROT and maximum TDS height between weak and strong and violent tornadoes. Again, a TDS must be located in the same spot as a tornado vortex signature, otherwise it's a false alarm. In this example, notice that this area of lowered correlation coefficient does not correspond to a TVS. As a result, this TDS is illegitimate. TDSs are also persistent features. They will not just show up for one scan and then completely disappear in the next. Lofted debris takes time to fall out of the sky, so even after a tornado has dissipated, a debris signature is often present in correlation coefficient data, albeit less concentrated and intense. On the other hand, not all tornadoes produce a TDS. Some tornadoes may not be strong enough to loft debris to the height of the radar beam, or they may traverse areas with very little debris to loft. In these situations, you may not be able to confirm that a tornado is in progress just from radar data, but when a legitimate TDS is present, a tornado is definitely occurring. While correlation coefficient provides the most effective way to see lofted debris via radar, differential reflectivity also has utility in this regard. The random orientation and irregular shape of tornado debris typically yields an area of low differential reflectivity coincident with the tornado vortex signature. In addition, intense, damaging tornadoes can exhibit a reflectivity feature called a debris ball. This is a small area of enhanced reflectivity coincident with the TVS at the tip of a supercell's hook echo. The large size and concentration of lofted debris in and around a tornado returns an increased amount of energy to the radar, which yields enhanced reflectivity. On rare occasion, very little precipitation may wrap around a supercell's mesocyclone, creating what's called a low reflectivity hook echo. In this case, the first sign of a tornado may be a debris ball that appears to be detached from the parent supercell. So, the underlying message is that if you're unsure whether or not a rotational signature is legitimate, use multiple radar products to confirm as well as the rules of thumb we discussed. Let's take a look at a couple examples. Let's say you're out chasing and you're approaching this storm. We can clearly see that it's a supercell. It has the classic V notch or flying eagle. It has a robust reflectivity core with very tight reflectivity gradients along its outer edges, and it has a clear kidney bean shape with a little bit of an appendage on its west or southwest flank. Then you notice this rotational signature, but you're not sure if it's legitimate. Let's go through our checklist. The first question you can ask is it in the right part of the storm? If the answer is no, you can usually disregard the signature altogether. In this case, the answer is yes. It's clearly coincident with the supercells appendage. But let's go through our other rules of thumb to make sure. Is it symmetric across a radial? Yes, it's clearly split in half along a radial, with our enhanced inbounds on one side and enhanced outbounds on the other. Has it been persistent? If we go back a few minutes, we can see that there's been some sort of rotation in that area of the storm for multiple scans now, so yes, it has been persistent. Does it have vertical continuity? If we go up in tilts, we do see some sort of rotational signature all the way up to tilt 4. So we've been able to check all of our boxes. Where's our radar? Down to the south of the storm, so this is definitely a legitimate cyclonic rotational signature, and with a maximum inbound velocity of negative 32.4 miles per hour and a maximum outbound velocity of 76.1 miles per hour, that gives us a delta V of over 108 miles per hour at a distance of about 60 miles from the radar, which satisfies the criterion for a tornado vortex signature. Can we confirm a tornado with this TVS? Taking a look at correlation coefficient, we don't see a concentrated area of lowered values coincident with the TVS. Although we do have lowered values here, they're part of this broader area of lowered CC, rather than a concentrated area of significantly lowered CC compared to areas around it. You could also look at differential reflectivity and spectrum width, but unfortunately this particular archive is missing those products. So there's not enough evidence to confirm a tornado debris signature and therefore a tornado with this couplet, but it's clearly a legitimate tornado vortex signature. How about another one? Here, again, we have a supercell with an apparent cyclonic rotational signature. Right away, however, we can see that it's not in the right part of the storm. Instead of being co-located with the supercell's appendage, it's situated on the edge of the forward flank. This should immediately tell you that this signature is bogus, but to make sure, let's go through our checklist. Is it symmetric across a radial? Yes, it actually is. Has it been persistent? Going back a few scans, it seems to appear out of nowhere with little sign of any pre-existing rotation, so no, it has not been persistent. Does it have vertical continuity? No. As we go up in tilts, there's no evidence of any mesocyclone or vortex in the vertical. So, while at first glance it appears to be rotation, it fails a number of points on our checklist and therefore is not a valid vortex signature.
Seats are now available for our 2027 Storm Chasing Tour. It's 8 full days of storm chasing, and the coaches on this tour are Trey Greenwood, Cameron Nixon, Kyle Gillette, and Hunter, folks. It is a lineup filled with absolute all-stars, and if you've ever wanted to go out storm chasing but you're not quite sure, or if you're just looking for a once-in-a-lifetime experience, this is definitely something you'll want to check out. Click the link in the description below for more information.
Close visual observation of a supercell can provide clues that tornado genesis is about to occur, but there are a few radar signatures that can tip you off as well. The first of these is called a differential reflectivity arc, or ZDR arc for short, which is an area of increased differential reflectivity that usually occurs on the right edge, which is typically the southern edge, of a supercell's forward flank downdraft along the reflectivity gradient. The ZDR arc occurs due to a preponderance of oblate or flattened raindrops that become confined to this region, a process called size sorting. The mechanism behind this size sorting process is the veering and strengthening of the winds with height, i.e. vertical wind shear, that occurs in supercell environments, as smaller raindrops that fall with lesser velocity are ejected farther from their source region than larger raindrops that fall more quickly. On the same token, the ZDR arc is tied to storm relative helicity, which is essentially a measure of the potential for cyclonic updraft rotation in supercells, generally below 3 kilometers above ground level. Storm relative helicity is an estimate of streamwise vorticity in the environment. Vertical wind shear creates horizontal, rotating tubes of air, which is a manifestation of horizontal vorticity or spin. When the wind feeding into a storm blows parallel to these tubes, the wind itself is spinning and the vorticity is considered streamwise. When the wind blows perpendicular to these tubes, the wind itself is not spinning and the vorticity is considered crosswise. Streamwise vorticity ingested by a storm induces updraft rotation from the get-go, whereas many storm scale processes must occur before an updraft in a crosswise vorticity environment can attain rotation. Think of it as a quarterback throwing a football to a wide receiver. If the quarterback throws the ball with a perfect spiral, the wide receiver can easily catch the ball and run it into the end zone for a touchdown. This is akin to streamwise vorticity. In contrast, if the quarterback throws a wobbly ball, the wide receiver may have to bobble the ball a bit before bringing it in, making the catch more complicated. This is akin to crosswise vorticity. Streamwise vorticity is much more favorable for inducing supercell tornado genesis than crosswise vorticity. Therefore, because the ZDR arc is tied to environmental storm relative helicity and streamwise vorticity, a ZDR arc can be a sign that tornado genesis may soon occur. The development of a ZDR arc can signal that a storm is experiencing increasing storm relative helicity and potentially greater streamwise vorticity ingestion, both precursors to tornado production. In addition, the separation between the ZDR arc and a feature called a KDP foot can indicate that tornado genesis is imminent. A KDP foot is an area of enhanced specific differential phase that represents the heaviest precipitation within the supercell's core. Like the ZDR arc, the KDP foot arises from size sorting induced by vertical wind shear. Leffler and Kumjian 2018 came up with a separation vector drawn from the centroid of the KDP foot to the centroid of the ZDR arc. They determined that the separation vector's magnitude, i.e. the distance between the centroid of the ZDR arc and the centroid of the KDP foot, tends to maximize around the time of tornado genesis. They also found that the separation vector tends to become more perpendicular to storm motion leading up to tornado genesis, and that both storm relative helicity and streamwise vorticity tend to increase with increasing perpendicularity between the separation vector and storm motion. When the separation vector and the storm motion vector are more parallel to each other, the vorticity is more crosswise. In this example, reflectivity is on the top left, storm relative velocity is on the top right, differential reflectivity is on the bottom left, and specific differential phase is on the bottom right. The ZDR arc and its centroid, along with the KDP foot and its centroid, are denoted as in the previous graphic. The separation vector, abbreviated SV, and storm motion vector, abbreviated SM, are displayed off to the side of the supercell in the reflectivity panel with red and blue arrows respectively. The time relative to tornado genesis is given in the top right corner. Notice how the separation vector and storm motion vector become more perpendicular with time leading up to tornado genesis. In fact, in the scan just 3 minutes before tornado genesis, the two vectors are nearly perfectly perpendicular to each other, indicating a shift to almost purely streamwise vorticity ingested by the supercell, and the tornado begins shortly thereafter. Mini supercells, especially those in more tropical environments, including those near tropical cyclones or their remnants, tend to display a mesocyclonic velocity enhancement signature, or VES, which is a small region of enhanced velocities greater than about 35 miles per hour between 7 and 14,000 feet above ground level on the right flank of a mesocyclone. VESs occur when mini supercells deviate from the mean flow, which yields an asymmetric velocity pattern within the mesocyclone, and they tend to be located above the low-level inflow region and co-located with the low-level mesocyclone and hook echo. Velocity values within the VES tend to maximize 1 to 4 volume scans prior to tornado genesis. Just like tornado genesis, certain radar signatures can provide clues that tornado dissipation is about to take place. Many of you may be familiar with the occlusion process of a cyclic tornadic supercell. This occurs as the rear flank downdraft wraps completely around the low-level mesocyclone, cutting it off from the warm, moist inflow needed to sustain tornado production. As this occurs, you'll often see the TVS begin to turn to the left of its previous track on radar, sometimes even making a full loop before dissipating. A new low-level mesocyclone often develops close to where the old one was, leading to renewed tornado genesis. Always be aware of the potential for leftward deviation near the end of a tornado's life cycle, as this can happen without warning and can lead to a perilous situation if you're located north of a tornado. In addition, several polarimetric signatures can develop in the lead-up to tornado dissipation. As described in Siegel et al. 2022, a decrease in intensity or disruption of the ZDR arc can be a sign that negative buoyancy is impacting the near-surface environment beneath the mesocyclone, which is unfavorable for tornado maintenance. This can also be a harbinger of decreasing near-supercell storm relative helicity. A decreasing angle between storm motion and the separation vector we just discussed can also indicate that tornado dissipation is imminent. Finally, precipitation within the hook echo tends to increase in intensity before tornado dissipation, which is often illustrated by an increase in KDP.
Remember to check out those links in the description below, and then watch another video.